Hello everyone, welcome back to our YouTube channel. Today we have a very special guest with us, Dr. Sachin Dev Verma, Assistant Professor here at IISER Bhopal, Department of Chemistry, and also the Faculty Advisor of our very own Chemistry Club. Hello sir.
Hello.
Thank you for your time that you are giving to us and for joining our podcast.
Thank you for inviting me.
So, sir, could you briefly walk us through your journey from joining IISER Bhopal, from your school days to joining IISER Bhopal and becoming a faculty here at IISER Bhopal?
Okay, so I come from a very humble background. So my father was the first generation who got formal education in our family,
Okay.
and my mother was very smart and intelligent, but she did not have any formal education. But she understood how important it is to get educated. So all our siblings, we are 6 siblings, all got very good education. 4 of us are in teaching profession.
Okay.
So my elder sister is a professor of Sanskrit in one of the colleges in UP, and another sister is also in a primary school teacher. My elder brother is also a scientific instructor in a technical institute, and I'm here as an assistant professor. So we already had a good motivation to study, go for higher studies, and do something in education field to teach others. So that motivation was already there, but I did not have any idea of what to do in future till I was in my MSc, and I tried different fields. So my background is physics,
Okay.
but before physics I enrolled in masters in mathematics. I was not really interested in mathematics, but that was the only course available in our city. So I had to move to a different city to get into MSc in physics. And then I got into JNU for PhD. And then I got to know what research is, what are the fields that I can work in. So everything I learned about research and particularly science was from my PhD supervisor, Professor Soban Sen.
Okay.
So he trained me to be a good teacher and a good scientist. And then I had a couple of postdocs in the US. One was in University of South Carolina with Professor Mark Berg. So I moved from experimental physical chemistry to theoretical. And then I moved to UC Irvine in California. There I came back to experiments again using 2D IR spectroscopy. And then I got a very prestigious Marie Curie fellowship to work with Professor Aksharao in Cavendish Laboratory in Cambridge University. And there I explored many different ideas in physics, in physical chemistry, in materials. And my current research is the combination of the work that I did in Cambridge and what I learned in my PhD. So using both ideas, I'm mixing and matching different things here.
Sir. That's very interesting. Your story is very. So from your childhood, you were surrounded with that environment of studying. So from your childhood, you were interested in science, or you had interest in some other subject, and then gradually you became more interested towards science.
So I was already interested in science. I always got better marks in physics, but my plan was to become a district magistrate.
Okay.
After 12th, I asked my father that I want to be an IAS officer. So I would like to enroll in Bachelor of Arts, and on the side I will prepare for UPSC coaching. By the time I qualify or reach the final year and pass the BA course, I would be prepared enough to write the UPSC exam, and hopefully I would qualify. And then my father said, no, only science.
Okay.
So then I got into BSc and then MSc, and in PhD I really got into research. What really got me into laser spectroscopy and excited state dynamics on those things.
Okay.
During my PhD only I understood what research is and how I can learn different techniques to understand fundamental processes in molecules and materials.
So sir, could you tell us about some of your hobbies, what you like to do when you are free?
So right now I don't get much free time, but when I used to write poetry.
Okay.
And right now I try to take out some time during weekends to play cricket. I like to play cricket, badminton, table tennis,
Okay.
read poetry, write poetry, but time is not much now. So, but if I get free time, then and also the frame of mind, I would really love to write more poetry.
More
than that.
poetries. That's very interesting. I had this for the very first time.
Thank you.
Most of professors say that they like to play cricket.
Yeah, I also like to play cricket.
Yes, sir.
And although we don't get as much time to practice as we would like to, but just to stay fit and
Yeah. And our department is also very encouraging about
yeah,
cricket.
so we have our own chemistry premier league
Yes,
every
sir.
year. So few faculty members and a lot of students take part into that.
Yeah, yes, sir.
It's a fun time of the year,
Yes, sir.
organizing that and playing in that.
Yes. So, sir, could you describe us briefly about your research, so the students get to know more idea about what exactly your lab works on?
Okay, so for me personally, the most interesting part of our research is instrument building.
Okay.
So we make optical microscope and spectrometers, and we use those techniques to understand how the nanostructures grow and what they do in their excited state if exposed to light.
Okay.
So these nanostructures have very interesting properties, that their electronic properties change as their size changes. For example, if you take quantum dots. So if quantum dots is in smaller size, it will interact with light or emit light at lower wavelength, higher
Yes, sir.
energy. If quantum dots are of bigger size, they will interact with light or emit light at higher wavelengths.
Higher.
So if you change the size, you change their properties. And their application is in solar cells and light emitting diodes and such. So suppose you want to make a pure green LED out of these quantum dots. And when you synthesize these quantum dots, inherently there will be a distribution of sizes.
Yes, sir.
So if you want to have average size of 6 nanometer, you will have some of 4 nanometer, some of 8 nanometer. So their optoelectronic properties are also distributed over a range of wavelengths. So you get mixed colors. You don't get pure green color.
Yes, sir.
So how to get pure green color? If you can minimize their size distribution, make it very narrow,
Yeah.
like
then
5 nanometer plus minus 1 nanometer or something like that. Narrower is better for purity of the color. You can minimize the heterogeneity by understanding how they grow. If you can
Okay.
control their growth mechanism, you can only control the growth mechanism when you understand the growth mechanism. So we have developed interferometric scattering microscopy. We are not the inventors. There are many people who are working on that. It was started or made it popular by Professor Vahid Sandogdhar in Max Planck Institute of Science of Light or something, and Professor Philip Kugura in University of Oxford. We also build it here, and using that technique, we can see how these nanostructures grow in size in real time. So when they are small, we send some light to it. Some light is scattered, so we get certain amplitude of scattered light.
Okay.
If the particles are small, the scattered light is small in intensity, and when the particles gets bigger,
Yes,
then
sir.
the scattering of light is also increased. So by looking at the scattering of light of these particles, we can see how the small particles grow into bigger particles.
Okay.
So that gives us the information about what is their nucleation rate, what is their autocatalytic growth rate. So we get the kinetic information out of this technique. And then we have coupled this iSCAT microscopy with fluctuation correlation spectroscopy, which is an equilibrium technique. So basically what it does, we create a small room and look inside that room with light. Whenever a particle enters that room, we know that particle is inside, and however long the particle is inside, it gives us scattering. Once it is out, it loses the signal.
Loses the scattering.
So we can see when the particle is coming in and when the particle is coming out, and measure the scattered light as a function of time at equilibrium. So we get these kind of fluctuations, which has information of their entry and exit.
Okay.
And from there, we can obtain how long these particles take to cross this small room. And that tells us about their diffusion coefficient. So from diffusion coefficient, using Stokes-Einstein relationship, we can obtain their hydrodynamic radius.
Okay.
So we measure the kinetic rates
Kinetic rates
of the growth of the reaction. Once they are grown, then we measure their diffusion coefficient and correlate it with their sizes. So we are trying to minimize the size as much as possible by controlling their growth
rate. That's very interesting, sir. Very interesting research area.
Thank you.
Yes.
And these particles are applicable in solar cells,
Yes, sir.
and light emitting diodes, sensors, and things.
Yes, as you mentioned that these particles are. So your lab is also working on energy nanoparticles.
Yes.
So could you explain us how these energy nanoparticles can act as a source of renewable and sustainable energy source?
Okay, so as currently we all know what is going on in terms of the oil and
Middle East crisis.
fossil fuel things. So it's better if we start to look for alternative
energy
renewable energy sources
Yes.
more aggressively to
Yes.
avoid such situations in future or minimize the effect of such situation in future. So solar energy harvestation is one of the very powerful field. Sun is always shining. As long as sun is there, we are there. So it will always shine. It will
Yes.
only get brighter and brighter. So it's a lot of energy we can harness. If we can use solar energy to generate our required electricity demand, then we will reduce our dependency on fossil fuel. So
Yes,
solar
sir.
cells are one of the application of these energy materials that we are working on.
Okay.
So we are trying to understand what happens when you excite any semiconductor which makes the solar cell with energy higher than the band gap.
Okay.
So if you give any energy higher than the band gap, the semiconductor will absorb the energy. But the electrons that are being excited will be with very high kinetic energy, and then they lose that high energy, excess energy, as heat. It is not converted into electricity.
Yeah.
So we are trying to find out ways to slow down this energy
Really-
dissipation process,
Okay.
so that we will have enough time to collect this extra energy and increase the efficiency of solar cells. So hot carrier
Okay.
relaxation.
Okay.
Hot carriers cool down very fast.
Very fast.
We
yes,
don't
sir.
have enough time to extract hot carriers. If we can slow them down to the point where we can extract them, then we can increase the open circuit voltage of the solar cell, and we can make use of that extra energy that otherwise is lost as heat to the lattice.
Okay. So we can reduce that the band. Will increase the band gap. So
Not the band gap. Band gap remains the same.
Yes, sir.
So that extra energy that they absorb above the band gap,
Above
which
the-
is lost,
we
can
are
make
trying
use
to
of.
use that energy.
We can, in principle, we can use it, but in practice, we are not.
We lose that energy.
Yeah.
Okay. So this is also very interesting. Sir.
And on similar kind of materials like perovskites,
Perovskites.
they are very good for light emitting diodes,
Yeah.
and
So-
many different quantum dots that are also useful for light emitting diodes. Samsung is making quantum LEDs,
quantum LEDs.
and there is some TV or computer monitor that is made from QLED. So these quantum dots are very interesting. Their property change as you change the size. So you can make them blue emitting, green emitting, red emitting just by changing the size.
Okay.
Same material, only the size changes.
Size changes
and
and,
the color
property
changes.
color changes and the property changes.
Yeah.
And you can do different things.
Different things. And we are trying to understand how they grow, how we can control the size, and most importantly, how we can control the heterogeneity in size to ensure the color will be pure if they are used in LEDs.
And many more new applications would be there then.
Many more new applications. Yes.
So, sir, suppose a student who is interested in physical chemistry. So, what are the core skills he should be focusing from the third year onwards, and when they get to know that they are interested in physical chemistry, so that they can succeed in this field of physical chemistry?
So physical chemistry is very
broad,
vast.
yes,
So
sir.
you have spectroscopy, you have electrochemistry, and there are many different fields that you can work in. Most important thing to be good at physical chemistry would be a very good understanding of physics and mathematics.
Okay.
Not in our IISERs, but in many universities and state colleges, chemistry students don't focus on physics and mathematics much.
Yes, sir.
They are only interested in organic chemistry,
It's
and
a general trend. Like
maybe some in organic chemistry. Very few people would be interested in physical chemistry just because they are not interested in physics and mathematics.
yes.
So
sir.
if you are interested in physical chemistry, then you have to have a decent level of understanding of physics and mathematics.
Okay.
If you don't have, you may
Develop that understanding with
develop
time.
that understanding with time. But to be good at physical chemistry or any area within the physical chemistry,
Yes.
you must have a decent level of understanding of physics and mathematics, particularly calculus.
Okay.
So
Because in schools also we see that when we learn physical chemistry, we generally mug up formulas
Yeah.
and do the numericals and get marks in physical chemistry.
Because except few states in India like West Bengal and Kerala and maybe Tamil Nadu and Andhra Pradesh,
Yes,
not
sir.
many other states, particularly in North Belt, focus is not on physics and physics and mathematics if you are taking chemistry as a
Chemistry
major.
is a major.
But in good university like DU and other places, to some extent JNU also, they make sure that you have enough exposure to maths and physics, even if you are studying chemistry. But majority of the state colleges and state universities, chemistry means organic chemistry,
Okay.
unfortunately.
And in organic chemistry is all about mugging up and.
No, it's also very interesting. I'm not
Actually,
trying
it's
to.
interesting, but people often feel that in organic chemistry is all about exceptions.
Organic chemistry could be very interesting if the teacher is good,
Yes, sir.
but it requires different aptitude than what physical chemistry
Physical
requires.
chemistry. Yeah, physical chemistry requires a little bit of maths and basic understanding.
More
of,
logical and reasoning and
a basic understanding of
then-
math and physics.
Definitely. My background is physics.
Yes, sir.
So I did not get much exposure to chemistry after my second year of BSc.
Okay.
After that, I had no education in chemistry. So, but I could pick up chemistry back when I joined chemistry department here.
Okay. So, sir, one last question. How has your experience been so far as the advisor of chemistry club of IISER Bhopal?
I have been learning quite a lot of things from interaction with students like you than I would have learned otherwise. So when you teach a class, you are teaching a set of students who are in receiving end, whatever you are teaching. Some of them will ask questions, but not much of a back and forth
Okay.
discussions
Yes,
happen.
sir.
Although I try to have it in my classes, but in general, students are not really open to
Questions.
question what you are
Yes, sir.
teaching. But when interacting with the students out of the classroom in a spirit of organizing something or making an event possible or something,
sir.
then there is exchange of ideas.
Yes,
I
sir.
may think this is correct. Students would think, no, this may not be correct, the
Yes,
other way is
sir.
correct. And sometimes students are more creative than I am. So I'm learning a lot of new things from students who are running the chemistry club. And I'm sure they are also trying to understand the perspective of a faculty community, that what can be done, what cannot be done, particularly when we are organizing any outreach.
Yes, sir.
And the students will come up with a list of experiments that these are the
These are the
experiments we want to do. All are exciting experiments, but there may be some backlash because the danger involved in some of the experiments, which students seems to not
Yes, sir. This
see. For them, it's if we can do it inside the lab, we can do it outside the lab.
outside the lab as well.
But I have that understanding that if you do that and anything goes wrong,
Yeah.
then it comes to the organizing authorities, not the students. How did you allow to do that?
Yes,
So those
sir.
kind of things I think students are also learning. And running the club is becoming more and more engaging as we are getting bigger and bigger. So
Yes, sir.
I became a part of the club when the Andrea and Sahil was running
Okay.
it in 2021 or something. At that time, the club was only a part of Science Council.
Science Council.
So it was doing things that Science Council
Council
is
would do.
organizing,
Yeah.
helping them in doing events and things. After that, when Kumar Abhinav and Nishad Chhatre became the coordinator,
Coordinators, yes, sir.
and I was the faculty advisor, they were very energetic and enthusiastic that we should expand, we should do things on the behalf of the department rather than solely on the
on the
behalf
basis
of
of the
Science Council.
Science Council.
And luckily, we had our then head, Professor Vishal Rai, who
Yeah.
was also equally energetic and enthusiastic about the department and the club. So then we have the club formally become a part of the department. So now club runs or helps the department in organizing departmental events. More importantly, the talks that the club is organizing from external speakers, online, offline, both
Yes,
ways,
sir.
and informal interactions. So students get to interact with the external faculty members or internal faculty members, not only discussing the science, but how their life journey has been, why they got interested in science,
Yes,
what
sir.
are the pros to be in academic area, what are the cons to be in academics, all those
And
things,
in a
all
more,
those
I
interactions.
would say, in a more friendly way, students get to know these things.
Yeah, so
Like sometimes from a perspective of a senior friend or an elder brother, I can say, because eh, when you are meeting a professor or some senior faculty inside a classroom, then the scenario is completely different. When you
correct.
meet such faculties and professors outside the classroom and in some such events where they can share their thoughts,
Correct.
the understanding level is very different at that point.
So it's more like a friendly chat rather than interacting with a professor of so and so institution.
Yes, sir.
So that way, I think club is growing, and both me and the people like you who are running the club are learning from each other. So it had been a very good experience being a part of the chemistry club.
Thank
so
you
far.
so much, sir,
Thank you,
for
thank
being the
you.
faculty advisor of this club
Thank
and
you, thank you
guiding
so
us
much.
in every moment of our life. Whenever we require your help, you're always there to help us. Thank you for that.
Thank
sir.
you, thank you.
Thank you for this.
My
podcast.
pleasure.
Thank you.